would discuss how to write efficient Cypher queries. I hope that at least most of the audience is familiar with Cypher or has some experience with graph databases. So let's get started. All right, I think that everybody can agree that what we want from our database, and it can be a graph database or a relational one or a document store, everybody is trying to get their queries to run as fast as they can, low latency. They want to process as many queries as they can, high throughput. And usually we want this all to work nicely with a low memory footprint. And this is challenging, both in terms of the database author, but also from the perspective of the user. And this is where query optimization kicks in. So to understand how can we achieve the performance that we're after, we need to dig a little bit deeper and understand what actually affects the performance, what can be tuned, and how can we go about doing this. And so with most databases, those that are queryable with a query language, the database task or a specific component within the database called the planner, who is responsible for transforming a query, specifically in our case, a Cypher-based query, into an execution plan, basically a set of operations that the database is going to have to run in order to compute the answer that you're looking for. And so an execution plan is basically a tree of operations. You can think about those operations as building blocks that you can compose in different ways, and each block is responsible for accomplishing a single task. I said that the planner is responsible for producing this plan, and data flows through the plan. One operation passes a record, a container of data, from one to another. Those records that end up at the very end of the plan, those would be returned back to the user as the final result set. Hopefully, the planner does a great job producing an efficient plan, but that's not entirely true, or that's not always the case. We, as a database authors, try to produce a highly efficient, a highly sophisticated planner, but there's a limit to where we can take the optimizations to. And either planners make mistakes or planners don't have enough information to produce an efficient plan. One side note to take here is that there could be multiple different plans, each one with different performance characteristics, but they all would be able to produce the same result for a given query. And so in this talk, we're going to investigate different plans for different queries, and the utilities that FalkorDB provides with the database regarding query optimization and reasoning about execution plans are two commands. One is the explain, which would give us an execution plan for a query without actually running the query. And so we're just getting the plan without running it. This is done usually if you want to just review what's the plan for a given query. The other and more powerful analytical utility is the profiler, which would not only give you the plan, but it would run it and profile it. And we're going to investigate a few profiles outputs in a moment. The profile includes for every operation the number of records it produced and how much time overall did the database spend executing each and every one of the different operations. So you can see an example in this slide for 3 operations and their profiling information. So to get things into perspective, or just to give us some ground to work with, we are going to work with a data model, a simple data model where we have 3 different types of entities. We're going to have nodes representing passengers, flights, and airports. A passenger boards a flight arrives at an airport, and a flight departs from an airport. This is the data model that we're going to be working with. And so to start out simple, just to illustrate some basic ideas, let's try and answer the simple question of figuring out how many airports do I have in my graph. And so we run this command, graph.profile. We provide the graph ID, in this case, flights, followed by the Cypher query. And it's a simple one. Match a node with the alias A. Its label is airport. And then just count 1 for every encountered airport. And this is the plan that was produced pretty straightforward. The way that we read execution plan is from bottom up. And so the first operation in this plan is at line 3, node by label scan. And this operation would basically scan through every node of a specific label. And so we're scanning through all of the airport nodes in the graph. We can see that this operation produced just over 10,000 records, meaning more than 10,000 airport nodes. And the time that the database spent doing so was 18 milliseconds. Follow up, the aggregation operation, which would perform the count, and finally producing the results. And so this is straightforward, but the database can actually do better. And it's not obvious in this case how to get there. This has to do with some semantics and the way that aggregation works. But if we were to rewrite this query, an optimization would kick in. And so the only change here is instead of return count 1, we're saying return count A. And basically count evaluates the value A. In case it is null, the count is not increased. And this is the thin line to understand here. And so the planner, seeing this, was able to produce a more efficient execution plan, one which doesn't actually does any counting. It just brings up some internal statistics and just spits out that statistics. And we can see that the overall time spent in computing this is less than a millisecond compared to the previous version, which took around 36 milliseconds. So a huge difference with just a small modification, and it's not always obvious. How to go about this? Well, if you have some expectations saying, oh, I'm just doing a count for some specific node type and I'm getting this after 36 milliseconds, that doesn't seem reasonable. Let me inspect the execution plan, and then you're seeing that all of this work is being done. That doesn't make too much sense. Then you can be on the lookout to try and optimize. Moving past this simple question, let's try and answer a different one. And so the new question is, which flights can take me from Salt Lake City to Washington? And usually people would come up with this type of a query where we have a graph traversal where we start at some airport, let's call this node S, and we're looking for departing flights, and the flight needs to arrive at Washington, which is another airport. And so we follow up with a where clause, just saying S needs to be Salt Lake City and T needs to be Washington, and we just return the flights connecting those two different airports. So looking at the plan for this query, we can see that there's a node by label scan. Once again, we're searching for the specific airport, Salt Lake City. This is line 7 right here. We've scanned through all of the airports looking for a specific one. Here's the filter, filtering out all of the airports but Salt Lake City. We found one after spending roughly 40 milliseconds. And then we follow up with traversals. We're going through S to find all of the departing flights. And then for every flight, we want to see where it lands. This is the target airport. And we need to see if that target airport is Washington. And so we see that we spend a lot of time doing a lot of work, which might seem reasonable, but definitely we don't want to be scanning through each source airport. We don't want to filter each airport that we've landed in. And so what can be done to improve? So this is what basically happened. Started at Salt Lake after finding it, find each departing flight, see where it arrived. Did it arrive at Washington? Yes, no. If yes, then return the flight. Throughout the process, we're going to see the summary of latency and throughput of each variation of the query. And so this trivial one has a mean latency of 13.7 milliseconds. And the overall throughput, QPS queries per second, we can run roughly 120. This is on my development machine. So this is the baseline. We start here. So the first optimization would be to say, I want to find S and T only once. Basically, we say find S, Salt Lake, find T before you start traversing. And so this where clause right here serves as a barrier for the planner, telling the planner, you must find S and T before you traverse. And so when you're getting to this match, S and T are already bounded. The values for S and T is discovered. And now you can start traversing. And so the plan changes. We see here that we find T, Washington, by doing a full node scan with a filter, and then another node by label scan for Salt Lake. And those two, at this point in time, those are disjoint nodes, and we need to combine them using the Cartesian product, which would yield just one tuple. Then we are going through, or the planner decided to expand from S to find all of the departing flights. And the important thing to note here is this expand into, which previously was a conditional traverse. Expand into occurs when we're traversing between two nodes that are already bounded. And so what the planner does, or this operation does, is just checking if an edge exists between those two. And this is a little bit cheaper than doing pure traversal. So we can see that the time that it took to expand into to be evaluated is just 54 milliseconds compared to the previous version, which we've spent 54 milliseconds doing filter, but we've completely removed this extra conditional traverse, removing 121 milliseconds down. And so
Roy, sorry to interrupt you. We just got a question that I think is very relevant to where you are in the conversation. The question is, are the display times real, measured, or estimates of the planner?
These are real measurements done at one time. These are not estimations. This is information collected as the query was running.
Excellent. Thank you.
Okay. So this new variation just checks if an edge exists. It doesn't check if we've reached Washington. We just check that if there's an edge connecting the current discovered flight to the already bounded Washington edge. And this is a little bit cheaper. And so the updated latency and throughput, we can see that the median dropped from 13 to 5. QPS throughput raised by 11. And we got a nice speed up. Nothing too fancy, but nice. Moving on, usually you should create indices for attributes that you're filtering on. And so if you remember this passkey label scan and then the filter, we want to replace this with an index seek. And this is exactly what's happening here. We've created an index, and now finding S and T is extremely fast, just consulting with the index. And so just finding those had dropped well below 1 millisecond. Once again, turning back to the summary, we can see, for example, that the minimum latency had improved by another millisecond. Median latency also dropped. The throughput didn't really change, maybe some degradation, but once again, this is my development machine, and the dataset is not big enough for all of those changes to show real impact. If we were dealing with huge datasets, then my assumption is we would have seen greater improvement. But still, create indices. This is not to discourage you from creating indices when they are in need. Okay, this one is a little bit more non-trivial. The idea here is to exploit the data model. And so what we see here is when we're doing the traversal, going from Salt Lake through a departure edge, we are guaranteed by our data model that a departure edge is going to resolve in a flight node. These are guarantees that you as a user need to enforce. But if you're enforcing those, then it is implicit that this F node is going to be of type flight. And if that's indeed the case, we can remove the label flight. And by doing so, we're removing a little bit of extra work that the database had done to ensure that indeed this edge had resulted in a flight node. Because this is guaranteed by the data model, we can actually remove this and improve performance. So basically, we can't really see the change in the plan. We're still going from S to F, but there's no extra validation or extra effort to make sure that F is a flight labeled node. This indeed impacts performance. Max latency dropped by 5 milliseconds. Average latency dropped by 1 milliseconds. Throughput increased. And we're continuing on. This change here says that whenever you're introducing scalars to a query, like the term Salt Lake City or Washington, D.C., these should be introduced in the form of parameters. Usually, you need to think about your query as a template, which can be reused over and over again, just under a different set of parameters. And by doing so, you're better utilizing the database internal caching system for queries. That's not to say that the result set is cached, but some processes that are happening within the database, like query validation, execution plan, construction, at least some parts of it, can be reused and skipped because we've already seen and processed this specific template. The only thing that is left is to evaluate the parameters. So using parameters, I don't think that made a huge difference on the performance, but still, it is an important feature to take advantage of. Lastly, this query had always returned the flight node in its entirety. And this might be reasonable depending on the application, what type of data it needs. But let's assume that the user or the application only cares for the flight number. And so if that's the case, there's no real reason to return the entire node. By returning exactly what we need, we're relieving or reducing network overhead. Some extra steps that are happening within the database are skipped, and usually memory is also reduced. And so turning back to the summary, by just returning the specific flight number instead of the entire flight node, we see a huge jump in performance, specifically in throughput. And this doesn't just affect the database side. This also affects the client. And the client that was used to measure those metrics were FalkorDB's Python client. And so whenever we're returning some value, the Python client needs to parse it and prepare the Python version of either the scalar, which could be a string or a number or an array or a node object or an edge object. And so by returning an integer instead of a node, we're removing a lot of heavy lifting and extra processing from the client parsing logic. I think this concludes this specific question of finding flights between Salt Lake City and Washington. Moving on to the next.
Roy, before you do start to interrupt, I think there's a few questions that were raised here that are really important before we move forward. Do you mind taking them for a few minutes?
Yes, sure, of course. No problem.
So the first one is, how long does creating the index normally take?
That really depends. It depends on the type of values being indexed. It depends on how much data is being indexed. I don't have a number that I can give you saying, oh, to index one string, it takes X amount of time. What I can say is that index creation is an asynchronous process. And so you can start out without an index, as we did here. We had the graph already constructed, we've queried it, we've decided that we want to create an index to improve performance. Issuing this command to create an index kicks off an asynchronous process within the database for populating the index in a background type of a procedure. While the index is being constructed, you can continue on querying your graph, and you can continue on making modifications to it while the index is being constructed. So sorry for not giving a clear number. It depends on the volume of data and the type of data being indexed.
Super. The second question was, in the context of multi-tenancy, do you prefer using node labels or properties to distinguish tenants? And how does the choice influence query efficiency?
That's a good question. It usually comes up when dealing with data modeling. And usually my answer is, you know what? Can you maybe elaborate? I'm going to try and answer the question as is, but I would like to better understand what do you mean by multi-tenancy. But before I get my elaborations, I can say that when it comes to data modeling and deciding between labels and attributes, I think that the better approach is whatever feels natural. The value of creating a label like a passenger or a flight is that you're doubling down on the fact that you have this entity. It's an actual entity. You can quickly filter out all of the nodes with a given label. You can create constraint against a specific label. You can create an indexing labels. So there are some constructs within the database that are within the resolution of a label, unlike attributes. So usually when I'm dealing with data modeling, my answer usually is whatever feels more natural or more reasonable when you're thinking about your data. How do you conceive it as a graph? It should when you're coming to one of your coworkers and you're saying, yes, I have this data laid out as a graph. Usually they have some vision of how things are laid out and how things are connected to one another and which attributes are associated with each entity. And it's this first impression that is usually the natural one. And this is the one that I usually go with.
Excellent. Just before we continue, the next question is, could you give us the size, meaning number of nodes and number of relations of the database that you've displayed and the times that have been calculated upon that?
I can try and give you the overall numbers. Let me quickly get this. Lights. So we have here almost 3 million nodes. And in terms of edges, we have here 5.5 million edges. In terms of timings, I'm not certain. I'm not sure exactly what are you asking for. Can you repeat this last part of the question regarding the timings?
I could maybe let's continue with your presentation. We'll clarify that and revisit that, circle back to that question.
Sure. Okay. Okay. So the last question that we will be dealing here with is the question of connectivity or reachability. And so the idea here is to say, suppose I have a passenger that boarded at some flight, or we have his flight history. So we know that he boarded flight 1 and 2, and those flights land at specific airports. We want to know if there's a path from each one of those airports that he visited, if he could have taken a direct flight or a two-leg trip and reach Heathrow, the Heathrow airport in the UK. So this is basically the question. And the query to figure this out is this one. We have our passenger. We're going to do a variable length traversal with a minimum length of 4 and a maximum length of 6. We're going to see why in a moment. And we want to reach Heathrow Airport. Why 4 or minimum 4, maximum 6 is because one hop is to get from the passenger to a flight. This is 1. Flight to an airport, that's 2. And then departure from the airport, 3. And landing at Heathrow, that's 4. And we allow a second leg, which means suppose we haven't reached Heathrow, we've reached some other airport. And so we need to depart and arrive. So an extra 2 hops. And this is the query. And what's important to understand with the situation is, once again, has to do with the data model. And it's not always trivial for the planner to understand how does the data look like exactly, specifically with graphs, that there's a lot of sparsity or randomness in terms of the number of connections between any 2 given nodes. And so whenever the planner is presented with this traversal pattern, he noticed 2 things. He looks at the starting point, let's say the passenger is the starting point, and he notes that this node has both a label associated with it and the filter. So these are like probes for this specific node. It is labeled and there's a filter applied to it. The planner is looking at the other end of the traversal pattern. There he finds another node, which is also associated with a label, airport, and the filter. And so when the planner is trying to evaluate from which direction should I try and traverse this pattern, there's a tie here. There's no clear entry point, which is more beneficial, for it to start expanding from. And usually this is where hopefully you have more information about how your data is laid out to try and help the planner to make the right decision to start expanding from the node which would narrow down the search space. And so if we try and expand from Heathrow, because Heathrow is such a big airport, it's a huge hub, then it is very likely then that the fan out, the number of reachable nodes from it, is going to be quite big. And from there, we're going to expand further. So our search space is quite large. There's a lot of neighboring nodes that we would probably hit before we're arriving at our passenger. On the other hand, if we were to start with our passenger X, the fan out compared to Heathrow should be relatively much smaller. There are not too many nodes or too many flights possibly that this passenger had boarded. Here's another angle to think about this problem. Let's suppose that I have a binary tree where each node has exactly 2 children. And we want to find the path connecting the root to some leaf node. if we started at the root node and we try to find T, depending on our traversal strategy, let's say we're doing depth first search, and we always go to the right, then at the worst case, depending on the positioning, we might be visiting every single edge in the graph before, or in the tree, before we have reached our target leaf. On the other hand, if we reverse the search pattern, we start at the bottom of the leaf and we traverse upwards towards the root, then it's just a handful of edges. In this case, it's log n, the depth or the height of the tree. And this is exactly what is happening here. And so this variation forces the planner, once again, with a with clause, it forces the planner to start out with hetero. We're saying to the query, or the semantic says that hetero must be found before trying to do the variable length traversal. And in terms of results, execution time, it's a pure disaster. We can see that quickly after we found hetero, we're doing this expansion. It produced 500 million results. It took us about 900 seconds to compute, and then each one of those 500 million reachable nodes needs to be evaluated if it's our passenger, which causes us to spend another 630 seconds just to learn that no, Heathrow is not reachable from any of the airports that this passenger had visited. So this is going like root to leaf. The other variation is traversing from the passenger to Heathrow, and in this case, we found the passenger using an index scan. We did the variable length traversal, which didn't. Wait, one moment. I think I have an error here. Yeah, didn't find anything. Why didn't find anything? Yeah, didn't find anything because it's not reachable. Didn't took us anything less than 1 millisecond, and this entire query took less than a millisecond compared to minutes on the other variation. With that, I would like to conclude and take any questions if there are any.
Great. First of all, thank you, Roy. I'd like to start with the first question that we got from Pavan. How do you optimize filters on patterns? For example, if I want to check if A is a friend of B's, are there indexing strategies that are available?
Okay. So these are two different ideas, I think. Filters and trying to see if a node has a friend relationship with another node. Applying filters, let me just give an example of a filter. Yeah, I think that most of the filters here are pretty simple. But let me quickly try and see if I can compose something real quick here. Okay, just move things to the side here. Match P person, and let's say friend of some other person, Z, and then where? Let's do P dot age greater than 12. Let's do 30. And P dot, I don't know, height, doesn't matter, greater than 1. This is centimeters. And Z dot, let's do, I don't know, let's say a person has a score greater than 90, and so on and so forth. Applying the filters it takes time. Basically, what happens usually is that we're constructing a tree out of those filters. This becomes one big tree, capturing the different filters, and then the tree is broken down to the most smallest component. In this case, p.age greater than 32. This is one component. We can break this because there is an AND. If I were to change this AND to an OR, then I cannot break this filter into subfilters because of the OR semantics. But because there are ANDs, I can break each one and evaluate each filter individually. After the filters are being broken down into the most smallest one, then it's the planner responsibility to position those filters at the earliest point in time where they can be evaluated. And so if we look, for example, at a query with a filter, so we see that we're trying to find Salt Lake City, and the filter is applied right after we have an S node to inspect. Same thing goes with Washington. the filter to find a specific airport named Washington is applied right after the T node is available. And so it's placing those filters, and then if an index is available, trying to convert the filter to an index if one exists. And then you can take it even further. Those filters that were not being converted into index, they are now being rejoined. So you don't see filter followed by filter. We recompact them. So here, let's say that z.score was converted to an index, but p.age and p.height had been rejoined into one filter tree. And now there are other optimizations that say, because there's an and, there's a left side and the right-hand side of for the filter tree, we can say this is an and. So let me first just evaluate the cheapest part to evaluate. Let's say just getting the edge is cheaper than getting the height. Then let me evaluate the cheaper sub-branch. And if it is false, then the entire expression is false, and I can move on. So filters are interesting components in a database system. In terms of finding friend relationships, the way that we go about this, and this is pretty unique to Falkor. Let me quickly see if I can get a whiteboard just to explain. And this maybe touches on the decision between attributes and labels. I hope that, yes, I'm getting my whiteboard. Whenever you are creating a relationship type in FalkorDB, let's say this is the friend relationship, Falkor manages a sparse matrix for each relationship type. And let's say that I have here some node I, which is connected with a friend edge to some other node, let's call this one J. And let's say that I is associated with the I row of the matrix. So this row is representing this node. And let's say that column J, this is column J, is representing this node J that we have here. For me to know if there's a friend relationship between I and J, I just need to inspect this entry of the matrix. If the entry exists, then it contains the edge ID. Let's say the edge ID for this particular edge is 4. If, for example, there's no relation between, I don't know, there's no friend relationship between I and Z, then let's say this is the Z column, then if I'm inspecting this entry, then it will be missing from the matrix. And so this is exactly what happens with the expand into operation. It just inspects the corresponding row and columns, unlike conditional traverse that does matrix multiplication. So I hope I've managed to answer the question.
I think you did, right. In the interest of time, Roy, as I know that we have another session coming up in about 20 minutes, and because we actually got some questions on Discord as well, we could probably fill another hour with those questions. They're all really great questions. What we're going to do is let's take one final question. We're going to pull all the rest of the questions that we got, and we're going to respond individually over email to all of your questions after the session is over. And the last question that we got is, are these efficient query patterns applicable only to Falkor, or is it applicable to other graph databases that are available right now in the market?
I think that most of what I've touched on is applicable to most other vendors that are supporting Cypher. The only difference is, I mean, Cypher or Open Cypher is kind of standardized. It's the operations that are not standardized, and I think this is good. Each database comes with its own planner and its own set of building blocks. And so usually you would see similarity between the different operations that, for example, Falkor have and the operations that other Cypher supporting vendors have. But there are some situations where we would introduce our own proprietary operation that does something which is, I don't know, maybe specific or take advantage of our underlying internals. It's kind of, comparing between x86 and ARM. This is maybe a nice analogy. The same C code can be compiled to the different architectures. One has a rich set of operations, x86. The other one has a very narrow set of operations or building blocks that are not complex, but it's the simplicity and the composition of them that yields performance. But I think that suggestions such as use templates, think about the guarantees that you're getting from your data modeling, create indices. This is a bit obvious to say, but I think that most of what I've covered here is applicable to most vendors.
Excellent. I would like to maybe call everyone's attention that a lot of the discussions that we're holding actually happen on Discord. So I encourage you to hop on Discord to drop those questions. But the ones who put them here in the Q&A on Zoom are not lost. We're going to collate all of them later and answer them individually. Or if you don't mind, you can skip to the last slide just to let everybody know that we have several. We're going to start a cadence of workshops like these that are really hands-on. Some would be live coding, other would be more like how to get started, how to do certain things, some theory as well. The next one's coming up on March 18th. It's about building your first knowledge graph. If you're interested, check it out. It's on our website. Everybody who attended this session is going to get an invitation to this workshop before we send it out to everybody else. And a recording of this session will be made available probably in the next 48 hours on social media, Discord, and everything like that. So we really thank everybody for coming. We hope you had a good time. We're trying to make these workshops as practical as possible and to really give you some, I would say, tools and some of our knowledge to get you started on your projects. We hope to see you on Discord and hopefully in the next workshop. And thanks, Roy. We appreciate your time.
Thank you.